So let me do my best on that. It's not going to be overly thin because I am, as you know, terrible at this, the drawing part. The doing math part, less so. All right, so, oh man, that doesn't look so hot. So this one's a little bit of a different story because really it's kind of hard to see where this is going in terms of an overall shape. It does look like it has an exponential component to it, but is it going to be asymptotic? How do we know? You know, we don't really know that, right? So what you can do is just kind of ballpark it and say, well, okay, so it's probably going to go like something like this over the top and back down. But really, at that point, it doesn't matter. Because all I need is something to really look at when it comes to the base regions. All right. The idea here is that the thickness associated with it is along the y-axis. So that would be a dy. All right. So we're going to integrate this. Double integral using the original function, which I already forgot, x squared sine of pi y over 6. All right, in terms of an area, a base area, or not a base area, sorry, an area of the face of it. Let me just kind of sketch that out a little bit. All right, if I were to create arbitrary rectangles to get that, they would be along the x-axis, all right? So you would have little arbitrary, actually, let me do those vertically, those little tick marks I did, and using a much darker color. All right, so each one of these rectangles has a dx associated with it, all right? So this is, you just kind of imagine that if you're looking on this surface from this angle, it would be a late Calc 1, early Calc 2 question, area under the curve. What would you do? You'd take the function itself and you'd integrate it with respect to x because your thickness for each of these rectangles would be along the x-axis, right? And then you'd state its starting and its stopping point. It's going from 0 to 6. All right, so I'm integrating this with respect to x. So it's really just 1/3 x cubed sine pi y over 6 going from 0 to 6. All right. In terms of calculations, that's not too crazy. All right. So pop in the 6. I won't have to pop in the 0 because that's how math works. It'll zero out. So 216 over 3, geez, was that 72?
Yeah.
72 sine of just a pi. Oh wait, no, it's still pi y because it's in terms of x. All right. So now what we've done, because again, we have a slice here, and that's all well and good. We found the area of one sliver along the, if I were to take my knife and cut it down, starting with the y-axis, parallel to the x-axis, through the surface, I have the area of one of those slices. if I can get infinitely many of those, going from 0 to 6, I would have the volume of the entire surface. All right, so that's the next step. I have a dimension y, all right, because each one of those areas represented by 72 sine pi y over 6 has a thickness dy. If you multiply them together, you get a volume, all right? What I want to do is collect all the volumes going from 0 to 6, and if I do that, I'll have the total volume contained between the surface and the xy plane. All right, so integrate. So we're looking at, we have to divide by pi over 6, so 6 over pi.
432 over pi.
432, but it's negative, right?
No, because it's not. Oh, yeah, you're true. Yes, yes, it's not negative.
I wrote sine. Jeez. There's no excuse for that. Going from 0 to 6. All right, well, the cosine of pi is -1, so it's 432. Oh, we're missing a pi. Over pi, right?
Yeah.
Yeah. Crikey. So 432 over pi. And then if I plug in a 0, I'm going to get, well, another 432 over pi. So 864 over pi. Yeah, cosine of 0 is 1, but you'd be subtracting the negative 432 over pi, so it becomes a plus. So 864 over pi. Hopefully that was the same as the other part.
So this just proves whether we take dx or dy first, we get the same answer.
Correct, as long as your bounds
Or the same.
are correct.
Or correct.
Yeah, because in this case we have a rectangular base area.
Mm-hmm.
If your base area is rectangular, beautiful, go for it. You could switch your x and y, you can switch your bounds, it doesn't matter. But if when the base area is not rectangular, it becomes like one of those other problems that we did.
Circle.
Like the circle one or the triangular area one. And, you know, a little funkier.
Can you explain what you just did?
Which part?
The whole thing.
After class?
Yeah, sure.
Yeah.
So-
That's the whole shebang. Yeah.
When you say something's parallel to the xy plane, you usually start by integrating that x. Would that be a fair way of thinking about
Yes.
it? And when you say it's parallel to the yz plane, you'd start at y.
Correct.
Would there be any point in which,
Like question 2, it says
Yeah.
in the xy plane.
yeah, we'll use something like that? Would you have to like integrate from the perspective of z then, or what would happen there?
What I see it as is whatever plane it's suggesting, like let's say XZ, draw a plane with the line X, the line Z, draw that plane, and you're kind of like scanning out. That's what I see it as.
Yeah, that's a good way to think about it. I mean, in the case of, you know, for this one here, we're saying you want to be bounded by the surface above the region in the XY plane. So you're not integrating through something that's parallel to a particular plane. We just want the region. It's just defining what region you're trying to find the volume of. All right. So in this case, I mean, for these problems, I could very well have said the same thing, and I didn't. But I could have said all of that above or in the XY plane, in which case we're really just talking about the XY plane being the base of whatever the surface's volume is going to contain. All right. So, and actually, sketch it out. Because you know that the length, width, and the height all have to be the same. So if we're looking at this in, you know, we have x, y, z, we can call this distance s, in which case this distance would be s, and so would this one. So really what we're looking for would be the volume that's beneath the surface of the plane z equals s, right? So you have a plane z equals s that's just kind of floating out there in space. Below that would be some, well, this is relying on my ability to draw, so hold on. Give me a hot sec here. So we'll have some square, oh, shockingly didn't do such a terrible job with that. I don't know that I could successfully get the XY plane below that, but imagine that there's an XY plane right here. You have the Z equals S plane. What you would need would just be the appropriate bounds to cut this off and make it a cube, because if you have a square base on your XY plane, project it up to a Z equation that has constant gradient, meaning that there's no change. It's a plane. It's horizontal with, or at least parallel to the XY plane. Then what you'd get would naturally be a cube. So it's just a question of where do I cut this off? All right. So if that's the case, I would need really this base region. All right. So when I'm integrating, and when I find my double integral, I have my z equals s formula, z equals s equation, constant. Wouldn't matter if I go with dx or dy. It's just I want to go in the x direction. I want to go from 0 to s, and I want to go in the y direction from 0 to the s value. So 0 to s, 0 to s. All right, so when I integrate, I would get sx on 0 to s, which would give us s squared. And then I would integrate that with respect to y, which would give me s squared y, also from 0 to s, in which case I get s cubed. All right, so double integral of the function over the region bounded by the curves in the xy plane. All right, so
Question was
It was like
pi minus y squared. and
no,
shit
this was
like-
the one where like some people were doing like 921.
Oh yeah, I think yeah. What? It's on the back of the handout just now.
It's
It's in the one we had to sell.
yeah, it's an old packet.
See what?
At that time.
Indeed.
Nah, but remember how we were getting like all the answers on that one? And she was just like, fuck it, we'll do the actual to do that seriously.
I'm not doing the same way you guys are figuring out.
Yeah.
Wait, what?
She legitimately said like, yeah, we're all getting different answers. Wait till your professor comes.
Oh,
She gave like she gave up. She
I
was
like,
like, nah. Oh, we were busting our balls. I kind of felt bad.
No, it's because we didn't know shit.
that's unfortunate.
Basic calculations.
All right, so 6 minus x plus 2y dx dy. Now we just need the bounds. That's always going to be a concern. All right. Now, this one, it's something that you can actually visualize, and the visualization part of it is probably the most important. Whether it ends up being a sketch that you draw, or if you're good enough that you can do it in your head, that's great, but that's not always going to be the case. All right, x equals y squared is a sideways parabola. All right, and 2 minus x is a linear function. So y-intercept of 2, x-intercept of 2, Now, scale-wise, this is going to be pretty terrible, but should look something generally like that. All right. So this is the base region that we're talking about if we were looking at an ordinary XY plane. All right. So no z-axis. All right. So this is something that you might see in a pre-calc course. All right. So the benefit of looking at this is that you get a truer sense of what your bounds are going to be. All right. Because I need to be able to work from left to right, bottom to top, depending on whether I want the dx to come first or the dy to come first. Right? If I want the dy to come first, then I want to go bottom to top, then left to right. Right? Because this is a relatively straightforward function, it really doesn't matter which way I go. But if you come across a situation where you have a function that in its given form is like a nightmare, you can't find its antiderivative, then you switch your variables so that you can actually have a fighting chance to be able to anti-differentiate. Right? We are going to need to know the intersection points. So again, we have x equals y squared and y equals 2 minus x. Little quick substitution, x equals 2 minus x quantity squared. So x would be equal to 4 minus, what, 4x plus x squared. All right, and so x squared minus 5x plus 4 would be equal to 0. X minus
Plus 1.
Minus 1 is minus 1.
Minus 5 plus 1.
or that, maybe? Okay. So x would be 1 or 4. All right, so we have some x values. We can go ahead and pop those in, but then the question becomes, did we constrain it the right way? All right, and so that's kind of the issue. Now, we have our two functions. I can also get the corresponding values of y for these two. So let me do that. Y would be, so we have one, right? And then, so I'll just put the 1 there, and then 2, negative 2. 4, negative 2. Thank you. All right. So we have numerical constraints that we can work off of, but we also have functions that we can live with. Right. This one is most conveniently written in x equals y squared form, because going the other way you get plus or minus and you get a radical involved. So what I'm going to do is rewrite this other function by solving it for y in terms x in terms of y. So we're looking at x equals 2 minus y. Is that right? Yeah. All right. So the way I structured my iterated integral is to deal with the x variable first. All right. So if that's the case, then what I want to do is I want to bound it between two functions. All right. So the innermost integral, you always want to bound between functions. The outermost, you want to bound between constants. All right, so we're restricting it between two functions and then adding the further restriction that that function has to exist only between particular constant values. All right, so looking at this from left to right, all right, so upper bound, lower bound. The lower bound would be the parabolic function. So y squared goes on the bottom. All right. The rightmost function is a linear function, which we call 2 minus y. Right? So now we have our constraints, but again, by defining the constraints in terms of functions, we're saying it has to exist within the parabola, or to the right of the parabola, to the left of the linear function, but we didn't say anything about the y values. Is it the entire interval, or maybe it's only part of it? Right? So for that, I would stipulate that the y values have to exist only between -2 and 1. Could have also gone the other way. Okay, so anti-differentiate, again, inside out. So I'll tackle this guy first. So we're looking at 6x minus a half x squared plus 2xy. Over the interval of y squared to 2 minus y. So 6 times 2 minus y minus 1/2 2 minus y plus 2y times 2 minus y.
The middle one's squared.
It is, yeah. Thanks. Minus 6y squared minus 1/2 y to the 4th plus 2y cubed. All right, so little cleaning, little housekeeping, and just see what the best way to go is. I think maybe factoring, then distributing it, then yeah, I think that's what I'm going to do. So for this piece here, I'm going to pull out a 2 minus y. It's going to give me a 6 minus 1/2 times 2 minus y plus 2y. 6 minus 1 plus 1/2 y plus 2y. One way or the other, I'm going to have to distribute, I'm going to have to FOIL, but hoping to clean it up a little bit more before I get that far. So 5 plus 5/2 y multiplied by the 2 minus y. So FOIL 10 plus, oh, that's going to clean up nicely, it looks like. 5y minus 5y, so minus 5 over 2y squared. Then I can subtract all the other stuff. Hardly any of which have like terms, which kind of sucks, but it is what it is. So 10, so -8.5 y, so that's -17/2. Y squared plus 1/2 y to the 4th. Oh, let me get in ascending order here. Minus 2y cubed plus 1/2 y to the 4th. All right. So now we're at the moment of truth. So from -2 to 1. And this is, it's dy. Okay. For some reason I had it in my mind that it was going to be dx, and I was like, why is this all in terms of y? All right, so now it goes to the calculator, and this is where all the hooting and hollering happened.
It's like a 13 point something.
Oops. Took my eye off the calculator for 1 second. Everything fell apart. Minus. I think I typed it in right. Well, let's see. 15.3.
Hey, let's go this guy.
She was doing it.
Yeah, she didn't get 15.3.
Well, we originally got 15.
Yeah, you changed it the whole time.
Hmm.
It's because we were debating why 2 minus y is greater than y squared.
Is this
Ah.
the substitution class?
Yeah. Fuck out.
So, it says evaluate the iterated integral by switching the order of integration. The idea behind this is, and it's actually kind of, well, funny's not the right word, but it's funny from my perspective, is that I accidentally gave this as a differential equation in my AP Calc class, and it's something that you wouldn't be able to do until you learn about Taylor series and Maclaurin series. So, yeah, they got the test. They looked at the problem and they were like, yeah, so about that one question, how do you do it? And my answer was, oh, my bad, you don't know how to do that yet. So I changed the question on the fly, but it was a perfect question for this particular topic because, yeah, you take a look at the problem and you say, I don't have the first idea how to integrate e to the x squared. Now, I just kind of gave you a sense, talking about Taylor and Maclaurin series. Maybe you like those sorts of things, maybe you don't. But with iterated integrals, you have the option to switch your variables. The issue is you're going to do it in a way that makes sense, right? So you can't just say, I'm going to switch my dx with my dy without accounting for the boundaries of integration, right? And it's not as simple as just saying, well, just switch the y with the 0 and the 1 with the 1 and call it a day, all right? So what we're going to do is just draw a quick sketch. Just xy axis. And we're going to take a look at each of these bounds individually, all right? So when we're taking a look at the innermost integral, now I just pull that out. The bounds are in terms of x. So that would mean that you have some x value that's equal to y, and you have some x value that's equal to 1. All right? So really what we're saying is integrate from x equals y to x equals 1. It's really the order in which you're doing your integration. All right, so that's all well and good. X equals y, what is that? That's a line. More popularly known as y equals x, but x equals y is the same thing. X equals 1 is a vertical line. All right, so what I want to do is just working from left to right, because we're integrating with respect to x, is I want to collect all the values, all the area that is starting with the line x equals y and ending with the line x equals 1. All right, so if I'm working from left to right, it's talking about all of these arbitrary rectangles, infinitely many of them, starting with, and again, it's area under the curve, so it's bounded naturally by the x-axis. But it's starting with the red line, the y equals x or x equals y, and then working its way over to the right until you get to x equals 1. Right? Then after that, you get into the part where the result is integrated in terms of y. So I'll do that in purple for those keeping score at home. Bless you. So the next step in the process is to integrate from, now this is with respect to y, so integrate from y equals 0 to y equals 1. All right, y equals 0 is the horizontal axis, and y equals 1 would be this line, horizontal line. All right, so with the same constraints, all right, so we're still operating under the assumption that these things are happening in conjunction with one another. I have to be integrating, or my region has to be bounded by x equals y and x equals 1 first, and then also between y equals 0 and y equals 1. So if we start off with y equals 0 and create arbitrary rectangles, we're talking about all of this area. But since I still have the same natural constraints from the first integral, I can't go past the line x equals y. All right? So that's the region I'm looking at. It takes a lot to really consider what's going on here. Right? Ultimately, that is the base area of some solid. Right? Because what a double integral does is it returns a volume. Right? So this would give us the collective areas under the curve of z equals e to the x squared. Right? With this particular base area in mind. So you got to imagine that there's some curve that's floating out in space, and underneath that curve is a whole lot of volume that's bounded by this triangular region. All right, so what I need to do is in order to be able to figure this out, I have to switch my bounds, well, ultimately I have to do that, but I have to switch my variables. I'm going to keep the e to the x squared, but I want it to be dy times dx. All right. The reason I want that is when you find a partial derivative or partial integral, you focus on the variable in question. This is the variable y. So I'm going to integrate with respect to y, which means everything else is treated as constant. All right. So this is just a glorified constant multiple in the world of y. Right. So if I have e to the x squared and I integrate that, it's just going to be e to the x squared times y. All right. Much easier than trying to actually anti-differentiate that. Then once we work that through, then we get to a point where, well, everything will be in terms of x. We'll have some numerical bounds that can go right in the calculator. All right, so we'll never get to a point where we actually have to figure out by hand what e to the x squared's antiderivative is. All right, But in order to do this, we go back to the drawing. Same natural constraints. All right. Now, what I want to do is I want to capture this same area, but first by looking at the y's. All right. So if that's the case, what I want to do is I want to go and start off at y equals 0. But I don't want to pass through this natural boundary. All right. So I'm going to start off at y equals 0. And I'm going to stop at the natural boundary of y equals x. Is there a question?
I was gonna ask, like, I didn't understand why you were doing that. Why were you going from the boundary 0 to x?
Because I want to capture this same region. And so in order to do that, the one logical place to start is to bound your y values between y equals 0 and y equals x, because that's going to capture this triangular region.
So you drew that triangular region out in the first place so that you can create new boundaries.
Correct.
So because the original boundaries did not work for us, that's why you changed them.
Correct. Aside from the instructions. But the instructions, you know, they tell you to switch the variables as part of a lesson, as part of a test, final exam, whatever. You may naturally decide, well, I want to switch the variables here because I can't do it the way it currently is. Right? But if I go from 0, if I go from y equals 0 to y equals x, right? You could even chuck it in there. You could write the little y equals, just to remind yourself what variable you're working with. That would bound my area between those two lines. Now, I'm actually just drawing it the way I want it to be, but really, if I'm saying it's going from between 0 and y equals x, well, technically, these blue horizontal lines would be infinite. They go off all the way to the right as far as you can go. So that's where the natural boundaries for x come into play. I'd have to say, all right, well, now what are my constraints for x? Well, here, it's a matter of saying, I want to go from x equals 0 to x equals 1, bearing in mind that these other constraints are in place. All right, so I'm stuck between y equals 0 and y equals x. But then also I want to be stuck between x equals 1 and 0 and x equals 1. And under those circumstances, if I start drawing my vertical rectangles, it's going to cover the same region just in a different way. All right, so this would go from 0 to 1. But again, if you want, make the little notation. It's really x equals. So then once you do that, and I'll write the clean version of it now. Once you do that, it's very easy to find the antiderivative. But you can also see how it wasn't simply just a matter of swapping, or I'll just swap dx with dy, so I'll swap my bound. It doesn't work that way. Right? You have to consider what it represents visually, geometrically. All right. So for the first one, if you didn't understand anything else from the last class, this would be one thing that you probably did understand. That would be, I'm taking the antiderivative of e to the x squared. There's no y in it. So that's like saying take the antiderivative of a constant. What would it be? The constant times the variable. So e to the x squared times y. Now that's happening over the interval of 0 to x. So we're going to have x e to the x squared, minus e to the x squared times 0, so I'm not going to write that. And then we can integrate that over the interval of 0 to 1. Now you can go to the calculator for this, but this actually also happens to be something that you could do by hand, right? Because this is actually simple U substitution, right? Because we know that the antiderivative of e to the x squared, e to the x squared, e to the x, antiderivative of e to the x is e to the x, all right? So derivative of e to the x is e to the x. So if you kind of make the assumption that the antiderivative is going to involve an e to the x squared, and then test it out through differentiation, what you'd come up with would be e to the x squared times 2x. That's double what I want. So slap a 1/2 in front of it. U sub on the fly. Also calculator. Nothing wrong with a calculator. Like I said, you know, I've said it a few times, I think. It's probably one of the reasons why many of you are taking my Calc 3 class rather than someone else's. I let you use a calculator, so use it. All right, so e to the 1 squared is just e, so 1/2 e, minus e to the 0 squared is 1, 1/2. All right, so it's kind of tough to visualize this. So GeoGebra comes in handy. I was working on it before. I don't think I saved my work, so I'll just have to do it on the fly. Yeah, it doesn't have a recovery mode. I'll just do it on the fly. All right, so we're going to compute the volume of the solid bounded by the surface and the 3 coordinate planes. All right, so the issue here is that we have something that, you know, based on the diagram, is looking very much like a sphere. Right? The 3 coordinate planes, if it's bounded, really I only want 1/4 of that sphere. And that's because if you assume that we're cutting it based off of the planes, the 3 planes, you're going to have the xy plane and the z plane as your natural bounds. And so that's naturally going to cut us off into quarters. All right. So in terms of a drawing, case in point. Let's see. I don't know. I've never successfully been able to draw this.
I'm sorry, Professor, I wanted to know, but because it's 3-dimensional, would it be an eighth of the sphere? Right? For a circle, it would be 1/4. For the sphere, it would be an eighth. Right?
Oh yeah, an eighth. Yeah, I was thinking of top half only, but yeah. Yeah. What it doesn't look like is 1/4 of a hemisphere, but that's what it's supposed to look like. Supposed to look like this.
But can't you, so to solve it, can't you just say like 4/3 pi and then just divide it by 8?
That's how we're going to check it.
Oh.
Confirm your answer with a geometric formula. Actually, we'll never get to a point in this one where we actually figure out the result of the integral. All we're going to do at this point is come up with the integral that could be used to find the associated volume. And the reason is, it's actually a simple reason. There's a better way to do it that involves spherical coordinates. Once we learn about those, it's going to make problems like this much easier. All right. So anyway, what I need to do is essentially what I did in the last one, just a little crazier. All right. So I need to find a double integral related to this bad boy with bounds for x and y. Now, at this point, because I'm saying, like I'm changing the nature of the problem to just indicate that we want an integral, it really doesn't matter whether I go with respect to x or with respect to y first. So I'm going to do dx dy. All right. So I need some x bounds. All right. So we really want to be thinking about what this would be like in 2 dimensions, because that's really going to help us establish what those boundaries ought to be, right? Because if you understand it in 2 dimensions, then it projects easily out into 3 dimensions. Really what you're looking at, bless you, if you chop this on the xy plane, you'd be looking at a circle, right? So on the xy plane, cross section is a circle, specifically x squared plus y squared equals 1. All right. The reason I know that is because this sphere is centered around the origin, and aside from getting into the numerical values, I mean, if you really want to do this the right way, you plug in a 0 for z, that puts you on the xy plane, and simplify solve. But that would, I mean, it's a roundabout way of getting this when you could really just use common sense. You say, well, it's going out 1 unit in each. If you guarantee that it's going out 1 unit in the y direction, and it's a sphere, it's also going out 1 unit in the z direction and 1 unit in the x direction. All right. So if that's the case, it's got a radius of 1, centered around the origin. Decompose it right down into the xy plane, and you have x squared plus y squared equals 1 without doing any algebra. All right. So if that's the case, then I could solve this for x. Normally it would be plus or minus, but since I only need part of it, really if you think about it, I don't need the whole circle, because x squared plus y squared equals 1 would be the whole shebang. If I did plus or minus, that would give me the whole shebang. I don't want the whole shebang. I only want half of the shebang. All right, so I'll take the top half. All right, but then I also want to split that, so that's a different story. Oh, I have it as x equals, so I want the right half. All right, so what I can do is go from 0, an x value of 0, to an x value of the square root of 1 minus y squared. All right, so no plus or minus, because if I did plus or minus here, it would go to the left and to the right. I only want to go to the right. So in terms of x values, what I'm doing is I'm bounding it. Here's x equals 0. And this whole part of it here, this semicircle, is the square root of 1 minus y squared. All right, so if I'm going from x value to x value, if I have these 2 constraints, I know them staying within a semicircle. All right, now for the y's, because the y's could be out of control. I can draw my vertical little rectangles. By the way, I say rectangles and you look at me, I'm clearly not drawing rectangles, but these are supposed to be rectangles with infinitesimal width, like Riemann sums. Right? So you're talking about squishing in as many rectangles as possible. So if you can get infinitely many rectangles in there, you could. I just denote that. I just visually describe that with vertical lines.
So it's like a Riemann sum?
Yeah, like those are when you did the rectangles under the curve. You drew like lots and lots of rectangles.
Oh, so you can get the area of it.
Yeah, exactly.
Why wasn't the bound 0 to 1?
So it could be 0 to 1, but that's going to give me a rectangular region. So if I did that, then I'd get way more than I need, and I'd somehow have to cut off all that extra stuff. So if I did 0 to 1 this way, and then 0 to 1 that way, well, 0 to 1 that way, I would get a whole lot of extra stuff that I don't need. And it's harder to actually cut all that stuff out. So it's just easier to make use of the curve itself as a natural boundary and then work off of numerical constants later on. So for the y's, since I only want a quarter of this circle, I'm going to start my y's and do a better job of that. I'll start my y's here, y equals 0, and then I can go up to y equals 1. So that's going to collect all these values. All right, so from 0 to 1. All right, while also naturally being contained within the curve. That's the important piece. All right, so by restricting, because again, I'm drawing the vertical lines the way I want them to, the way I want them to look. But they technically, when I say that I'm going from 0 to the curve, yeah, that's cool. Those lines could go on forever, you know. Or, well, in this case, they wouldn't because they're stuck within the curve. But I would get a lot of extra stuff here that I don't want, right? But if I bound it between 0 and 1, I'm creating natural boundaries, starting at 0, going to 1, but still within that curve. So the only thing I'm going to get is that 1/4 circle. All right. Now, projected out into space, you're going to get this piece of the surface, all right, and that's going to have an associated volume. So if you integrate this, which admittedly is not the easiest thing in the world, you'll get your solution.
When you say projected, how do you do that? Like when you put the last step, like when you go 0 and 1.
This is the third dimension.
Oh.
Yeah, because it's really, if you think about it, you have 3 dimensions: x, y, and z, right? So we're taking a collection of infinitesimal rectangle widths associated with x, then we're doing the same thing for y,
Right.
but then we have heights associated with each of those coming from this bad boy.
Gotcha.
Yeah.